So let us discuss the modern way of defining units, fundamental units. So let me go through that. We want to define units for all the magnitudes in physics. So we can start from the Newton's equation, F equal mass times acceleration. And let me use the notation of brackets to mean the dimensions of force, which must be the dimensions of mass times the dimensions of acceleration. And for mass, I do have m, and for acceleration, I have lt to the minus 2. So m, l, t means the magnitude, mass, length, and time. So what we need is definitely patterns for those three units, three magnitudes, sorry, and we have chosen these to call them kilogram, meter, and second. So we need to define patterns for these three. So how this was done in the past? So let me talk about the old definitions. Well, people use physical phenomena that were accessible to them. So, for instance, they would consider the rotation of the Earth in the beginning, or lately, it was the system of Sun and the planet Earth orbiting, and a fraction of the time that the Earth rotates around the Sun was the definition of a second. For the kilogram, well, in Paris there was an object that was defining the unit of mass, the kilogram. And also in Paris, okay, there was a stick that would correspond with what we call a meter. So here we have the three units, time, kilogram, and meter. Now, what is the problem with these three units? Well, the very first is that all these units are not accurate enough if you do really very precise measurement in your lab. The pattern, the unit that you use, is not precise enough. Second, they are not stable. So the mass in Paris was changing weight, or you may have dilatations of the stick, or the rotation of the Earth is not stable with hyperprecision. And more important, they are not reproducible. How do you do that? I mean, how do you do a kilogram in your lab? Well, you have to go to Paris, copy that weight, and take the copy with you to your lab. So, in a way, all these definitions, although they made sense in the past, they were not useful for modern science. So, at some point, in physics, the need to define a much better system of fundamental units was growing. So let me tell you, bypass the steps where we changed all these things into what is modern. There were several steps in the middle, but let me concentrate right away in the modern definitions of units. So what is the central idea? The central idea is that when we go to nature, we see some phenomena which are extremely universal, beyond a particular experiment. The obvious examples is the relativity, is the speed of light. So after 1905, the speed of light is understood as an axiom, which is given as the maximum speed of propagation of signals due to the work of Albert Einstein. So how can you accommodate with these things? So here is the very clever idea. So why don't we define only one basic unit, and then we take some phenomena like the speed of light that brings a relation between distance and time. So, and we postulate relations. That's extremely clever. So rather than defining 3 units completely independent, we define one basic unit and then we define relations. And this was on. So the first one that was introduced was the second. And the second was referred to a fundamental observation. And that was the atom of cesium. So what we do is we take the atom of cesium, which is identical in all the labs. We consider a very specific transition, the hyper-fine transition of a fundamental level, and we simply count periods of that transition. So we have a given frequency by nature, and we consider that our definition. So this, then I use the symbol define, 3 lines, not 2. So that was 192.631.770 periods of this fundamental transition. So let me write it, hyperfine transition in the fundamental level of cesium 133. We may consider that this is not precise enough, but for several reasons, and we may substitute that phenomenon from nature for something which is easier to implement, or it's better for other reasons. And this is under discussion. So people are considering whether this is the ultimate definition. But now how comes the magic? So we then define 1 meter as the distance which is traveled by light. Doesn't matter which light, because all light travels at the speed of light. That's a postulate of quantum mechanics. So we are accepting that nature has taken this postulate as a truth, an absolute truth of nature. It doesn't matter under any circumstance the speed of light. The maximum speeds are defined by the speed of light, and the speed of light is constant. So this is the distance traveled by light in, and the definition that was taken was exactly that, 792.458 seconds. So as you see, let me now change it. This is equivalent, absolutely equivalent, to defining the speed of light. So as a matter of fact, C now gets defined. And it is defined precisely at 299,792.458 meters per second. Obviously, no error. So imagine you do an experiment and you want to measure the speed of light. Well, you would need a stick, a meter, and you would need a second, a clock. The clock would be the cesium clock. But then, when you make the meter, actually the meter would be made with the speed of light. So there is no way to measure the speed of light. It's a definition, okay? Notice the 3 sides. So that is a gigantic step, because it needs to accept that relativity is an ultimate theory that will not be changing. Okay? This is what we are doing here. Now, in the 80s, this was the situation, whereas the kilogram was still a very clumsy definition. So what happened is that in the year 2019, the final step was done. So why don't we go and we define kilogram as a relation to the second and the meter. And this in this, now this is an assignment, so this is a definition. We define h, Planck constant, divided by 62607.015, 10 to the minus 34, meter squared sinus minus 1. And when we put everything here, we have a definition of. This is tantamount, okay, to defining h. And then h is defined exactly as this quantity, 6.6260715, 10 to the minus 34 kilograms, meters squared, 10 minus 1. So please note again this absolutely remarkable fact. We accept that both C and H, the fundamental constants needed for relativity and for quantum mechanics are a given number. They are fixed. They are not subject to change in time. We accept that this is an absolute truth of nature. What is also a little bit of a peculiarity is why in 2019, when these numbers were now absolutely fixed, this happened before, but this happened in 2019, why we chose this particular value of C. It's a definition. So actually we could take any value. Do you like to, to take 722 for the speed of light? That would be absolutely acceptable. Absolutely acceptable. The same for age. You can change. You can do whatever number would be equally good. The problem would be that if we don't take a number of this type close to the previous measurements of the speed of light using old units, then all our physics of the past would change. Whenever we would read a paper of the 19th century, we would not be able to read the units because they are different. So the very basic fact of why we have chosen these numbers is to maintain continuity with the previous science. Not to, we don't need to kill all our equipments, we can continue. But from now on, it's a much more precise. So these numbers were chosen to be more precise, more digits than any previous measurement. Okay? That's why you can make the continuity of this thing. So this is the fundamental fact. Now, let me argue that this has even a more profound consequence. So for that, let me go to the left. Let me erase this. I erase the past. And I move to the future. So what is accepted implicitly here? Okay? What is accepted, as I said, is that H and C are defined. So let me go back to the equations of Newton. Okay? So if I have M, L, and T, and I define T, and then I define L through C, and then with both of them, I go with H to mass, and there are no further relations. And we have used relativity and quantum mechanics. In a way, we are saying that there are no further changes of paradigm. So this was related to relativity, and this is related to quantum mechanics. So the ultimate theories that can be described with this way of proceeding are those that simultaneously obey C and H, and the language that we have found that describe all these things together is quantum field theory. So in a way, we're accepting that quantum field theory is the way of describing our world. Remember that in the old quantum physics, there would be some disagreement with relativity, some paradoxes. It is only when you bring the machinery of quantum field theory of particles, antiparticles, second quantization that really you have a consistent framework. Yet, there is a fundamental unit. So, could we think that there is a change of paradigm, something different, something where quantum field theory is no longer valid? Because there is a fundamental unit. So I repeat, relativity is conditioned by the fact that C is finite, it's not infinite, that there is a finite speed of light. Quantum mechanics is conditioned because H is not zero. There is a minimum unit of action. So what is left is that there is a fundamental unit, which is inaccessible beyond that. So that's indeed the idea that there is something at the fundamental scale. The only idea we have now is that this happens at the level where quantum gravity operates, and this will happen typically at the time of Planck, which is of the order of 10 minus 3 seconds. So maybe there, all the description we are using is no longer valid. Maybe there is a fundamental unit of time, maybe space-time is discrete, maybe the description of all the interactions are change It's no longer a continuum. We don't have differentiable manifolds. Maybe you have a discrete seed. Maybe you only deal with permutations, as some people have. So this is implicit. But still, all these things are at the fundamental level. But there are some refinements that can be made. So let me talk about two small refinements. The first is that if I'm accepting all these framework, so why do we need extra units for the charges of all the forces? This is an equality. Again, if I believe in this and I've defined M, L, and T, I have an indirect way of defining any charge which appears on the left. And indeed, I will do it on this little corner. These are called rational units. And this is what people do in high energy physics. What they do, for instance, is that if I have let me take as an example the electric charge, well, then automatically the electric charge is the same as M L T minus 2 times R squared cubed. And now I take the square root for this thing. So here I am. Okay. So the electric charge can be measured in the square root of kilograms, meters to the 3/2 divided by second. In particular, I could redo all these things, and because I'm in a new domain and I'm not matching my things with macroscopic events, why not redefine C and H to be 1? That's what we do. So this is why, although you have listened in your life about the electric charge, and you call it Coulomb, you never heard about the charge for strong interaction, which is color. You never heard a word for the charge of color, neither for the flavor of the weak interactions. We don't even have a word for that. So we are accepting this idea of relations, and we even push it further to define C and H to be 1 in that realm. You can always reconstruct this other way of doing it by substituting the values of C and H. And there is another, this is for let me say, the smallest energy physics in the fundamental interactions, but there is another extension, which is whenever you deal in the lab with macroscopic objects. And then, again, how do you do that? Well, the natural thing when you go to the macroscopic world is to be bold enough to accept that there is a definition of what is macroscopic versus microscopic. And the basic idea is that we have a number that connects the two worlds, and this is the Avogadro number that enters in the definition of a mole, okay, when we go to real macroscopic physics and chemistry and all the other domains of knowledge. So what we do there is that we simply have done the following. We have simply taken the Avogadro number to be defined. So again, 3 lines, and then it's 0, 2, 2, 1, 4, 0, 7, 6, 10 to the 23. It's an absolute number, no units here. So again, those are magnitudes, but the connection between the microscopic and microscopic and macroscopic world is a matter of numbers. It's a dimensionless. So this is why Na is defined and there is no units. There are other microscopic units. For instance, we now define the Boltzmann constant. We also define the ampere. All these numbers which are macroscopic, or the candela, are defined in different ways, in a way to avoid the relation to these fundamental units, okay, as they are done. So there is a final discussion, which is how you implement these things in the lab. So all these units must come together with a recommendation. You may define H, but how do I implement that in the lab? So you have to look for the best possible, more accurate experiment, and then, which is sensitive to H, and that is your reference for other experiments. You may consider, for instance, the quantum Hall effect as a way to introduce H in your laboratory. So after this presentation, you may see that it is likely we will stay with our units for a long time. unless they are not precise enough for certain experiments. Then maybe we change cesium, or maybe we change the recommendation of how to implement the unit in your laboratory. So, only one revolution waiting for us. That's it.